good morning, good midday or afternoon for everybody, depending on which time zone you are in. Today we have the pleasure of hosting Professor Lena Maier-Hein, who is working at the DKFZ, the German Cancer Research Center in the beautiful city of Heidelberg in South Germany. Yeah, Lena Maier-Hein is working mostly on imaging-related techniques, mostly for cancer research. And as in all of the research areas, we have lots of metrics and lots of benchmarks. And fitting to our usual series, they don't always do what we claim that they're doing or what we want them to do. And so today we will have her talk on metrics reloaded in the spirit of slow science and research. So yeah, we're looking forward for the talk. One last organizational comment. This talk is going to be recorded. You are free to ask questions during Lena's talk. If you prefer not to have your voice recorded, then just write them into the chat and we will read them for you. And apart from that, enjoy the talk.
Thank you so much. I'm really happy to be here because I really like the topic, the spirit of the seminar series. I'm Lena Maier-Hein. My background is computer science, but I work very closely with clinicians, so I have to basically make sure that both of the two worlds are satisfied, and this is not always the case, especially when we talk about metrics. Slow science is a really nice keyword, I think, and at the moment, from my perspective, we're doing a lot of fast science. I want to show you one example that really impressed me. Last year's paper, I've shown it in so many presentations already, but I really like this paper. So here, this was about COVID-19 detection. So what happened when the pandemic kicked in? A lot of people basically tried doing AI on whatever problem, in this case, detecting COVID-19 from the imaging data. And you see that they used a lot of publicly available data sets there, indicated by these bars, the yellow, blue, etc. bars. Now comes the problem. If you look very closely at what data was really used for these papers, on the x-axis, you see a lot of papers, dozens of papers. You see that systematically the yellow and the blue data set were combined. And these actually have very interesting properties. So the control group, the pneumonia control group, no COVID, comprises only children, and the other data set comprises only adults. So this means that basically the pattern that an algorithm needs to learn is to distinguish children from adults, right? And this is a very good example, I think, of fast science. So people just download data sets, apply the algorithm to it and report results. And I think we really need to change this. We need to think more properly about what we're actually doing, because at the moment, from my perspective, we're not solving the right problems. I mean, I can only speak for the biomedical domain, but this probably also holds true for other domains. So actually, I'm a surgical data scientist. This is not what I'm going to talk about today. If you're interested about the general topic, yeah, have a look at these papers that I'm citing here. But I'm doing this because death within 30 days after surgery was actually identified to be the third biggest contributor to death worldwide, which I think is quite a big thing. So this is what I'm normally working on. But in this particular presentation, I've tried to abstract from the specific surgical problems. And I will talk a bit more generically about metrics. The starting point of all this was that, we have all these AI research, but from a biomedical perspective, I can say that whatever happens in research, all these great success stories, they don't translate to any benefit or in clinical practice yet. Well, any is maybe too harsh, but mostly they do not translate to any benefit. So today I want to talk specifically about metrics. And all of this started actually when my team basically looked more into challenges. I mean, in the end, challenges today, competitions are used to measure scientific progress in the field. I think most of the audience's background is computer science, so you're well aware. There's a lot of impact of challenges, fame given to the researcher, prize money, etc. So we started a few years back, and I will not talk about this long, no worries. Actually, I have I've created a lot of new slides for this specific presentation. So hopefully I will stick to my time. I will make sure. So we started with this question, is the winner really the best? Special thanks to Annika and Matthias from my team, but also to all the collaborators in the study. I will make a long story very short and just show you one example of what's happening with respect to metrics. If you're interested, read the Nature Communications paper for the details. So here you see basically, or you will see in a second, the results of a real world challenge that is very famous, many citations, happens regularly. You see the 13 best ranked algorithms in this challenge. And now you see a lot of challenge design choices. So what design choices do you need to make? You need to decide on a metric. You need to decide whether you aggregate the rank or the metric value. So either the classical procedure is to first compute the metric values over all cases, then aggregate. But this, for example, has the disadvantage that you cannot deal with nonce. So you can also compute a rank per image and then aggregate. So this is a design choice. And then, of course, the aggregation operator is important. Now, if you play around with these strategies, you see that you obtain completely different rankings. And this has, of course, a lot of implications. I mean, if you don't make the challenge design transparent beforehand, you can cheat as an organizer because you don't want your competitor to win. So a lot of things we can conclude from there. But today I want to focus on the metrics. You see here we actually used 3 very commonly used metrics, and you see that the winner changed the ranks completely based on which metric we choose. So in other words, the choice of metrics is really important. Now, somebody who read our paper, or one of our metrics papers, brought up this Cobra Effect story, which I wasn't aware of before, and I really like it because I think it really hits the essence of what I'm trying to say. So in Vietnam, a while ago, there was a rat plague. And of course, the government was trying to get rid of rats, so they promised a monetary award for all rat tails. And what happened was that people, because they wanted to receive money, they cut off the rat tails, but it didn't kill the rats, because I thought, okay, if the rats reproduce, I can get more rat tails. And this, I think, is a very good example of a metric, a proxy, that doesn't really reflect what you're actually interested in. So in this case, the rat tail doesn't reflect the number of dead rats. And I think we have a similar problem in image analysis. So in image analysis, we ask questions given a reference, like the blue one here, dark blue, which prediction is better, or how good is a certain prediction? And we have to express this somehow mathematically, right? And this is a challenge by itself. I mean, I come also a little bit from sports, and there the metrics are simpler, right? If you want to measure the speed of someone, you just stop the time and then you have exactly what you're interested in. And in image analysis, it can be very different, especially if you have an underlying domain interest. And I will give you some examples in the following. Before I want to make this terminology straight, I'm sure many of you are aware, but let's just bring everyone on the same page. So on the x-axis, you see different modalities. This is not important to us. This just should illustrate that what I'm saying now generalizes over modalities. In this case, computed tomography, microscopy, endoscopy. So in the following, we will look at 4 different what we call problem categories. So actually, this is classification at different scales. So first one is simple, classification at image level, I think is clear. And then the semantic segmentation is basically a classification at pixel level. Now, the problem with semantic segmentation is that it cannot distinguish different instances from each other. We will see this in a second, which is why there's also instance segmentation, where we have an explicit differentiation of instances. And if you're not really interested in exact boundaries, you can do object detection instead. So that's basically like instance segmentation, but using rough shapes to approximate the location. So we look at these in combination because they share a lot of properties, and we try to depict in this diagram. So let's go through it. It's not totally straightforward. So here you see the different categories, from image level classification to instance segmentation. Regardless of what you do, you typically have a class probability. as an output, either on pixel level or on image level or on object level. And then typically what you do is thresholding. So you generate a threshold on your probabilistic output, for example, softmax output, and then you generate a confusion matrix based on this. The segmentation matrix problems have a special interest also in boundaries. Let's ignore this for a second. So I want to talk more about the classical classification metrics for a moment. So if you have a fixed confusion matrix, then you can apply what we call the single threshold counting metrics, which basically are based on counting true positives, negatives, false positives, negatives, and combining them in whatever way. So typical examples are sensitivity and specificity, accuracy, F1 scores. They're all based on one fixed confusion matrix. So alternatively, you can go for multi-threshold metrics, which basically work on a variable threshold. So to illustrate this here, some people argue, why would you choose a fixed threshold if you're interested about the general performance of your classifier? So let's not choose a maybe arbitrary decision threshold. So instead, you basically put the threshold over the continuous class scores. You vary the threshold, and then you can compute an ROC curve, which relates complementary properties, sensitivity and specificity in this case. Or if you work on object detection problems, you don't have true negatives, right? So you cannot use specificity. In this case you use precision. The positive predicted value is a synonym instead. And then you get these curves, and the areas under these curves give you the measure of performance. So one is best possible performance. Okay, now we've worked a lot in a larger consortium for the work I will show you today. And I can tell you that there was a lot of debate about these multi-threshold metrics versus the counting metrics that work on a fixed confusion matrix. And it turned out that it really depends on the community. So there have been a lot of, for example, biological experts, and they said, I don't care about multi-threshold metrics because I'm interested in applying the algorithm in a specific setting, and for this, this is of no use. I need a cutoff. Others say, well, why would you work with arbitrary cutoffs? You're interested in the inherent properties of your classifier. So I can already sneak peek that for this reason, we basically recommend using both. But one side note also on the cutoff, because I think most people, this is my observation, think automatically the cutoff should be the argmax. So in binary classification, above 0.5 should be positive, basically, below should be negative. And this is not necessarily a good strategy. There's multiple strategy, and one that is actually interesting in medicine is this one here. We call it metric at metric, basically. So for example, you may say, okay, when I assess the quality of a method for polyp detection, for colonoscopy, cancer screening, then I really need a guaranteed sensitivity, let's say of 0.98. Then you pick the sensitivity, and based on this, you optimize your cutoff, and you get a specific specificity at the chosen target value of sensitivity. So we discussed this at length actually in this paper, the Metrics Reloaded paper, the different strategies that you can have. But I think for now it's important to keep in mind that the argmax is not the only option that is available. Okay, so you saw in this diagram there's a lot of metrics out there. Actually, here's a word cloud of metrics that have been used in biomedical image analysis challenges. You see it's a lot of metrics, implying that it's not straightforward to actually choose a metric. And when we ask people, challenge organizers actually, why they chose metrics, the standard answer is, well, because it's commonly used. I mean, on the one hand, it's a good answer. On the other hand, just because something has been commonly done, it's not necessarily a good choice, right? I mean, this is, I guess, one of the things that this seminar series is about. So let's look a little bit into more detail. Here you see on the left-hand side the metrics that have been applied in image analysis, biomedical image analysis competitions, and you see, so we analyzed more than 500 competitions, and you see by far the dye similarity coefficient is the most widely used one. So what does it do? So in the following, the reference, for example, provided by a radiologist will always be depicted in dark blue and a prediction in orange. And this basically computes a value between 0 and 1, 0 meaning no overlap, 1 meaning perfect overlap. For the computer vision community, this is very closely related to the IOU. It's directly computable. There's only minor differences, but you can regard them as equivalent, basically. So this is the most widely used metric. Coming back to this question here, such problems, so imagine these are tumors in the brain, for example, such problems have typically been assessed with the dyes, but you see, I mean, if I asked the domain expert what is the better prediction, the orange one or the light blue one, I can guarantee you everybody would say the light blue one, which has a lower dye score. And the reason, of course, is that you're more interested to detect all the lesions, all the tumors, compared to basically getting only the big ones better in terms of pixel accuracy. And this is a big problem. I mean, it sounds so obvious. I mean, I would say, well, this is obviously either an instance segmentation problem or an object detection problem, but not a semantic segmentation problem, right? But this is not a concept that is widely spread, at least not widely enough, because often the problems are phrased as semantic segmentation problem. And I mean, I had a discussion with someone who actually contacted me because they wanted to organize a challenge, a clinician, and they had exactly this problem. And I told them this should be an instance segmentation problem. And then they told me they can't, just from an annotation perspective, it's too time consuming to phrase this as instance segmentation. And that's why they do a semantic segmentation. So there can be pragmatic reasons. I'm not sure if it's worth it, but okay. So we identified a lot of pitfalls. You can see, read the picture story paper by Annika on this. And the next step then, and this is not yet published, it will be released hopefully within the next couple of weeks, was to develop a taxonomy of pitfalls. I'm aware you cannot read them now. Don't worry. The message now is just that we have a taxonomy, and I will guide you through the pitfalls just now. So the first of the big blue points, that's the main categories, is the inappropriate phrasing of the problem. So I just gave you an example. Now I want to sneak peek a clinical example, not yet published, but I find it pretty cool. So it's actually Klaus, my husband, Klaus Maier, gave it to me. So here you see this is brain tumor segmentation, and they assessed a recall of 0.94. So at the voxel level, overall the images, the performance of the classifier is really good. So is the all the related metrics such as dyes, IOU, etc. Now, if you look at instance level, so again, this is really what we're interested about, right? This is different because if you look at the same person here, there's a small lesion right here that has been missed, right? So this is not reflected in the metric because of the other big tumor, but it's clinically highly relevant. And we can even put this relevance in numbers. So there's something that you call instance progress in medicine. So you basically want to know if from time point n to time point n plus 1, there's more instances now. In this case, more brain tumors. And despite the high performance of the segmentation algorithm, instance progress was not well detected. And this is not reflected in all the competitions, right? So these algorithms win challenges. It said, well, it's already, human level performance in terms of dyes or whatever, but this is clinically highly relevant and a big problem. Now you may say, well, okay, but boundary-based metrics may reflect this. So there's some metrics that don't look at overlap, such as dyes or IOU, which are totally, basically they ignore shape altogether. So then you can take boundary-based metrics, but they also have problems, right? So if you look at this example here, if you phrase the problem as a semantic segmentation problem, and you have two instances you have a prediction like this one here, then the boundary of the wrong instance will actually be used and confuse all the calculations. So again, this would be a point for phrasing the whole problem as an instance segmentation problem.
Lena, one quick question by one audience member. Could you again clarify the difference between semantic segmentation and instance segmentation?
Sure. Yeah, this is a very important.
Take some time to understand it in the beginning. Yeah.
Yeah, sure. I go back to the slide. One second. Terminology. Maybe that was too quick. Okay, so basically now we have to compare this row here, which is instance segmentation, to this row here, which is semantic segmentation. So in semantic segmentation, let's take binary for simplicity. You would only create binary masks, meaning this is the class and this is not the class. In instance segmentation, in addition to basically detecting the class, you can distinguish between different instances. So you would say, in this case, this is class type cell instance 1, class type cell instance 2, class type cell instance 3. And this was what makes it important. Any more questions on this? Does that clarify the question?
I hope it does. Yes, he says thanks. All right.
Okay, so then, you know, in instance segmentation, what you would do, this is actually part of our recommendation. So you would first basically compute the detection performance via classification metrics. So how many instances have you actually found? And then you can apply segmentation metrics per instance. And then you have both, right? And not just an overall measure over all voxels, basically. Okay, now let's talk a little bit about classification after segmentation. We're entering the second point, which I will focus on today, which is pitfalls related to the actual metric selection. And well, you see there's a lot of sub-points, and I definitely don't have time to cover them all. So what I'm doing now is cherry picking just to show you, the range of pitfalls that can actually occur. And this one, I think this is new, actually. It's not yet in our recommendation paper because, to be honest, the reason was that the core team of us, we're no calibration experts. So we thought maybe we can leave this out of the recommendation, but there was so much community request for recommendations also on calibration that we just included it now. We recruited some calibration experts, worked on it. So this needs to be finalized, but I will give you a general idea. So, okay, we talk about image level classification now. So let's say you get an image, you want to say cancer or no cancer, for example. So in this particular case, if you look here, you would get an ROC of 1. Perfect, because you can differentiate the two classes perfectly. Now, a clinician, especially from the prediction community, would say this is nonsense, because I need to know the real risk. I need to know when I have a classification problem, what is the real probability of that patient, for example, having cancer, because that has clinical implications. So even if, for example, the probability is way below 0.5, let's say 20% cancer is still a big thing, right? So this may have clinical implications. So this leads us to the topic of calibration, which basically means that your predicted class scores reflect the actual probability. Okay, so how is this done? And by the way, this is a good example here. After we talked about the cutoff, here a cutoff of 0.5 would have given very poor performance, right? Because in this case, you would need to set the cutoff at 0.515, but that's just on the side. Okay, so how do we assess calibration? Probably the most widely used metric is the expected calibration error. So what does it do? I mean, it's a not very trivial task to assess the confidence of a classifier, I can tell you. But what is currently being done is the following: you basically, for each, you have a validation set to assess your calibration capabilities, where you know the truth, and you know also the output of your classifiers. So the output, for example, could be 0.8. Now, if it's 0.8 or let's say 0.9, you're in this bin here, and you collect all the samples for which your algorithm set 0.9 or 0.8 to 1 basically. And then in this bin, the accuracy should be the same. So it should be an average of, well, 0.9 in this case. And this is basically done for all the bins. And then you take just the weighted average of the bins. Now comes the problem. This is taken or adapted from a really nice paper that will be presented at NeurIPS this year, actually, from Florian Bittner's team, who's also on the board now, luckily. Here, we assume a perfectly calibrated classifier, and all we do is we change the sample size. And you see that with this, the expected calibration error changes. I think this is really disturbing because it means, you know, you have this romantic idea that if your algorithm is properly calibrated, then you get a calibration error of 0, but this is not the case, especially not if you have a small sample size. So this is one problem, and another problem is the following. This is a bit complex. I don't have the time to explain this in detail, but you can look at the paper that I'm citing here, Evaluating Model Calibration and Classification, which I kind of stole the example of. I just color coded a bit to make it a bit more clearer. We did actually. Annika did most of the work. So I want to bring across the message. So when you do calibration, most people actually look at what I would call top label calibration. So this means you look at your prediction, you look at the confidence score, and actually at the class that you predicted, and then you do all the binning, etc. So this is basically top label calibration. What could be of much more interest is the canonical error, which basically means that if in a multi-class setting, let's say you have 3 classes, you really want to reflect the probabilities, the estimations, the uncertainty, the true probability. So you have to compare the whole vector, but this is not done in top level calibration. So there's one in between, which is basically marginalizes over classes. Again, I don't want to explain this in too much detail now. I just want to tell you the message, which is you may have an expected calibration error of 0 if you use top level or the class-wise calibration, but in reality, your uncertainties are not perfectly calibrated because you don't do canonical calibration. This needs to be taken into account. So again, why could this be clinically relevant? This, again, like in the example I mentioned before. So maybe you have a case in which also the second class means cancer. It's not the most likely outcome, but if it's a very aggressive cancer, probabilities are 0.3, you better want to know, right? And if there you are totally overconfident, underconfident, then that has large implications. So this needs to be taken into account. Okay, let's come to a bit more simple example. One that is quite widely known, but still I see so many publications that do it wrong. So I really want to mention it as well. Class imbalance. So typically I use the word prevalence when I refer to class frequencies. Here you see the classes are highly imbalanced. You would get actually an accuracy of 97% for a classifier that predicts only the dominant class. And this is, of course, very problematic. And this is because accuracy is a prevalence dependent metric. So I want to talk a little bit more about prevalence dependency, because to be honest, while working on this paper, this aspect became a little bit more clear to me. So let's say you have a classifier with a given fixed sensitivity and specificity. Sensitivity and specificity are always important because they basically reflect the inherent properties of a classifier. Maybe you have had this discussion with your family as well in your in the COVID-19 times, because COVID-19 tests would have a specific sensitivity and specificity, but then basically the probability of being positive or negative once you had a positive test depended on very much on the prevalence, which was a bit hard to explain for me to my family, because if the prevalence was low, even if you had a positive test, it was quite likely that you didn't have COVID. And this is because prevalence typically plays a key role. So these tests, of course, they don't want to provide numbers for a specific population, but they want to provide the inherent properties, which is, for example, sensitivity and specificity. Now, if you apply sensitivity and specificity to different data sets with different prevalences, I'm showing you an example here. Prevalence 50% basically means 50 positive, 50 negative cases, 90%, 90 positive, 10% negative cases. And then depending on this, if you use a prevalence-dependent metric, like accuracy, you get different results. If you use a prevalence-independent metric, you get the same result. And this may or may not be desired. This is important. It may actually be desired. You may want to know exactly, for example, the accuracy on your population. If this is what you want to know, then fine, take accuracy. But if you want to compare, for example, classifier across data sets, you should never take accuracy. It doesn't make sense if prevalences are different. And here, I'm sorry, I didn't introduce all the abbreviations because I don't have the time to introduce all the metrics. Just a little pitch for BA is balance accuracy. That's basically the sum of the sensitivities for the respective classes. So in the case of binary problems, it's sensitivity and specificity average. And expected cost is a metric that is pretty interesting. It's actually a generalization of accuracy, and also balanced accuracy has a very nice theoretical foundation. We will discuss it in a bit more depth in the upcoming version of the metrics reloaded paper. But it can be basically tuned to be prevalence independent. So you can provide the prevalences of your classes directly in the formula. All right. So maybe this now sounds like you should always use prevalence independent metrics, so just use metrics based on sensitivity and specificity. Well, that is also not the whole story. We played a lot around with, generating confusion matrices, and this is one of them. So here, I mean, if I asked you, is this a good classifier? What would you say? I mean, you would probably say, well, I mean, it gets most things right because the false ones, false positives and false negatives are, quite a few relative to the positives on the true ones, basically. On the other hand, if you look, this could well be a screening task also. So if you look at those cases that are found to be positive, that's basically false and true positives, then basically the positive predicted value is only about 0.5, right? So it's so I would say, the performance. Now, if you look at the metrics, you see sensitivity and specificity are really high, because sensitivity and specificity only look always in the respective rows. And this is really misleading, right? You should get really, imagine you report only sensitivity and specificity, you get really high values. And this is because these don't take the predictive values into account, the positive and the negative predictive value. So again, positive predictive value is actually precision. And this would be reflecting this column here. So you see, it's quite a complex topic. It's not so easy to say, well, always just do that. And then finally, last item on the list is the pitfalls related to the poor metric application. One example is provided here. You see there's a lot more on the list, but here you see a representative example. It's related to aggregation. So from my perspective, what I see a lot, at least in biomedicine, is that the hierarchical data structure is not well respected in validation. So people just aggregate over all images. So if you do this in this specific case, for example, you would get a DSC, a DICE of 0.8. But maybe you want to take into account that you have a lot of data from one specific patient, for example, because you do video-based analysis, then you don't want this patient to dominate your whole score, right? So then you need to aggregate hierarchically and you get a completely different value. And these are things that are very important when applying the metrics. A last example is this one, the inadequate metric reporting. So here you see, for example, for 5 different algorithms, the raw values. And we found in our analysis that a lot of challenges report only rankings. And actually, this is also something I see a lot in the computer vision community, to focus everything on tables. And this can be very misleading, I think, because in this case, we have two very different scenarios, right? In one case, the performance is very different of the algorithms. On the other hand, we actually drew the samples from the same distribution. They both lead to the same ranking. If you're interested in this topic, we published an open source toolkit on fixing these issues. So this is not part of Metrics Reloaded, but maybe have a look in case you want to do uncertainty aware results analysis. And of course, this is not just for challenges, right? It could just be the benchmarking of your algorithm compared to other algorithms. Okay, so maybe I brought the message across that the topic of metrics is not totally trivial. So there's a lot of aspects that need to be taken into account. And this is probably also why there's so much that goes wrong. So we founded this Metrics Reloaded consortium, which actually involves many key players around the world, both from industry and from academia. I especially want to thank the core team, Annika and Pau, also Patrick and Minou, who were really, great. I have to say that I was without kids for a week, and instead of going, on vacations, we organized a Metrics Reloading hacking week. So we just spent the whole week hacking the paper, which is very nerdy, but it was also fun and cool to have time to work on something very intensely. So now I want to pitch what we recommend in Metrics Reloaded in a few minutes. Of course, if you're interested, you should take a look at the paper.
Before that, there are 2 more questions from the last part. One is by Ben, who is asking on why the F1 score was low when sensitivity and specificity were at 0.99.
Yeah, so both the F1 score and the MCC are prevalence-dependent metrics, and they have the characteristic that they take the so-called predictive values into account. So predictive values means, given all the positives that were detected, or negative, same or negatives, that would be positive or negative predictive value, how many of them in percentage were actually positive. And this is something that neither sensitivity nor specificity answers. And MCC is actually an interesting metric because it basically, if any of the typical values that you're interested in, which is sensitivity, specificity, positive and negative predictive value, if any of them are low, MCC will also be low. So basically, if you have a high MCC, you kind of have the guarantee that all the different values are high, which is, I think, an attractive property. And well, F1 is a little bit similar. F1 is not for multi-class. F1 is applied per class, but it also basically incorporates the predictive value, which is why it's, that basically answers the question. Because if you remember the confusion matrix, then the predictive value, positive predictive value, was only 0.5, and F1 implicitly takes this into account. I hope this answered the question.
Right. Thanks. Yep.
Okay, so let's first talk about the concept. So we thought, okay, we want to be kind of modality independent, domain independent. So how can we do this? And our solution is what we call a problem fingerprint. So we try to extract everything that is relevant from a validation perspective from the problem. Then we have this problem fingerprint. And then based on this fingerprint, we make the recommendation. So what is this fingerprint? What does it cover? It covers, for example, domain interest. Is the user, the clinician, for example, interested in the boundary of a structure, in the volume of a structure, in the center line of a structure? I mean, that changes everything, right? Target structure related problems. How is the grid size? I mean, the size of the structures compared to the grid size. For example, if you have, very small structures and also no, not very high inter-rater variability, it doesn't make sense to take an overlap-based metric such as DICE or IOU at all. It doesn't make sense. Also, size variability plays a role. Dataset related properties such as class imbalance, for example, and also algorithm output related properties such as, do you have continuous scores available or not? I mean, this is generally the case in neural network approaches, but there's also some other approaches. If you don't get the scores, then of course this has implications with respect to the metrics that you can select. Okay, so we took, I don't know, definitely more than a year to generate these fingerprints in this large consortium. And then the recommendations are basically based on these fingerprints. So this is the bird's eye perspective. You see that you don't have to look at the details for now. It's just to bring the general concept across. So you see the different colors. That's the 4 problem classes: instance and semantic segmentation, image level classification, and object detection. And you see that paths do cross once in a while. And this is why we also look at them in one joint framework. And I will clarify what we do by zooming in. So let's start with image level classification. Here, the core of the recommendation is actually captured right here. Whenever you see a plus, there's actually a whole other decision tree that makes the actual guidance. But you can see in the green boxes what the results could be. So to give you that idea, we start by selecting a multi-class counting metric. This means even if you have a multi-class problem, let's say you want to distinguish 10 different classes, you can capture the performance in one single score. And I can maybe sneak peek that here, I'm a big fan of expected cost, which is prevalence independent if you want, or also of MCC for the reasons I just mentioned, because they give you that, MCC gives you that guarantee if it's high that none of the values is low. So the decision often boils down to the decision between the two. There's a special case when it's getting more complicated, which is when you want to apply costs. So for example, if you have ordinal variables, you want to classify the stage of cancer, for example, then you may want to say, well, confusing stage 1 and 4 is much more severe than confusing stage 1 and 2. Then you want to assign costs. So this is typically handled by the weighted coherence kappa, in case you've heard of it. I'm not a big fan of it, so I would definitely prefer expected cost, but all the details in the paper. Okay, now you have a multi-class metric. You have one metric that captures everything in one score. Now we argue that you additionally want to do a per class assessment, especially if you have, for example, rare classes, you want to really know the performance for each class. And this is captured in these two, S3 and S4. So the per class counting metric is basically, based on a fixed confusion matrix, based on a cutoff strategy. Often it just boils down to using the F beta score, like the F1 score per class. Then the multi-threshold metric, which typically implies you use AUROC in case you have true negatives or otherwise average precision. That's long story short. And then finally, if you want your output to be calibrated, you select the calibration metric. So that is the core recommendation for image level classification, for example. Then for semantic segmentation, it's a bit more easy. It's really combining two. And I have to say that after we recommend these common metrics, we also say, okay, now you can complement this with domain-specific metrics that basically reflect complementary needs. So in semantic segmentation, for example, volume-based metrics. But here we focus on the common metrics in this part of the tree. So in semantic segmentation, we basically argue you need an overlap-based metric. So most commonly, this will be the DICE, equivalent to IOU. If you have tubular structures, it will be centerline DICE instead, for example. And then you complement this typically with a boundary-based metric, sorry. And here the default recommendation, it depends again on the fingerprint. Often it will boil down to NSD, which is normalized surface distance, which has surface size, which has the great property that it can capture basically inter-rater variability. So if you know your contours are not exact, you can basically capture this in the metric. Okay, then we have the object detection and instance segmentation. Here we have two additional points that are important and that I think are maybe underestimated, but given now that I look at the time, I will skip this. Sorry about this. I had a nice example. And yeah, to conclude, the instance segmentation would only be the metrics for object detection, then complemented by segmentation metrics applied per instance. And you can read all the details in the paper. It will be uploaded soon for the latest version. So we basically ask for community feedback here to optimize our recommendations. We also have several recommendations for selected use cases. We're working on a tool to facilitate the user's experience and also on Steckbriefe profiles, metric profiles that give you all the pitfalls and limitations basically as a cheat sheet. This will be released also pretty soon. And with this, yeah, I hope I could show that maybe some of the problems that we have with respect to clinical translation of methods can be attributed to metrics. And I think we can make a difference there. Thank you.
Thank you very much for this whirlwind tour through the world of metrics. So always be aware, everybody, of the metrics you're using. Before we go to questions, one quick organizational comment for everybody who needs to leave early. There will not be a seminar next month. Instead, we hope to see a lot of you at our Neurons workshop, which will also be streamed online. And as usual, all of the recordings of the past talks and also of today's talks will be online on YouTube. So in case you need something to do in December, just rewatch our old seminar talks.